Section 4.5, Graphing Rational Functions. In this section, we're going to talk about graphing rational functions. Rational, if you recall, means fraction. Okay, and what we are particularly interested in fractions where the numerator and the denominator are both polynomials, where you have polynomial on the top and polynomial on the bottom. So graphing these functions is quite a bit different than graphing polynomials that we did a while back in this chapter. Graphing, if you recall, to graph polynomials, all we had to do was find the x and the y intercepts and find the extreme behavior, and then we basically connected all the dots in essence. Okay, but in this case things are going to be quite a bit different. So let's first talk about how we graph rational functions. I'll give you the steps first, and then we'll look at each step. Okay. The first thing we have to do when we graph rational functions, so let's say if you're given something like this, some rational function. So I'll just call it f of x, where you have a polynomial on the top and a polynomial on the bottom. Okay. So the first thing we want to do is we want to simplify the function. We always do that if you can cancel anything that cancels from the top and the bottom after we factor. So basically it means factor and cancel. Sometimes you cannot do either one, you cannot do that, but you should always try. The next thing you do is find the x and the y intercepts. And we know how to do that. To find the x-intercept, we set y to 0, and then to find the y-intercept, we set x to 0. And then we want to do is make sure that you remember if the x-intercept has multiplicity, things change, the graph will behave differently. For example, if it has even multiplicity, then the graph tends to turn at that point, at that x-intercept. If it has odd multiplicity, then if you recall, the graph flattens at that point. What we learned with polynomials still applies. Number 3, we want to find something called asymptotes. We want to find asymptotes, and there are 3 types of asymptotes we want to find. The vertical, MB is the horizontal, or slant, because you can't only have one or the other, and I'll explain more about this later. But there are 3 types of asymptotes: vertical, horizontal, and slant. But a problem can either have horizontal or slant, but can't have both. Okay, so this is what the game plan we want to follow. And sometimes the last step is, sometimes we may need, I'll put the word may need extra points to guide the graph. And that's not something you'll need all the time, but every once in a while you might need that. Okay, so this is what you need to do. And I'll also put one last thing: check to see if the graph crosses the horizontal asymptote or the slant asymptote. I'll abbreviate those. That's something we need to do. Okay, and I'll explain all of this in detail, but I just wanted to give you the steps down first. So these are the steps we follow when we have a rational function, where we have a function that is a fraction with a polynomial on the top and polynomial on the bottom. So please make sure you use these techniques accordingly. If they'd just given us a regular polynomial to graph without anything in the denominator, then we know how to do that. That's something we did in, I think, section 4.3 or 4.2. Okay, but in this case, because we have a fraction, the method is a little bit different. We know how to simplify. That's something we did in chapter 1. We know how to find x and the y intercepts. That we did in chapter 3 and also in chapter 4 when we were graphing polynomials. So let's talk about asymptotes. Okay, so the first thing I want to talk about is a vertical asymptote. Let me give you the definition of it, and then we'll talk a little bit more about it and how to find it. So what is a vertical asymptote? I'll abbreviate that VA. The vertical asymptote is a line y is equal to a, I'm sorry, x is equal to a, okay? Actually, let me write it differently. Here, let's do this. The line x is equal to a is a vertical asymptote if the graph increases or decreases without bounds, without bound, as x approaches a from both sides. Okay, so basically what that tells me is when we say a graph increases or decreases without bound, that means it gets really, really big, and when we are talking about infinite and minus infinite. Okay, as you get closer and closer to a, as x approaches a from both sides. So like what that means is, just to visually show you, let's say this is a, okay, I'll just draw a dotted line to show the vertical line. Okay, the line x is equal to a is a vertical line. We've talked about that, right, before in chapter 3. On this line, x values are always a, y values can be whatever you want it to be. So now there's lots of things that could happen here. As x approaches a, as you approach a from this side, so as x values get closer, okay, just to give you an actual example, let's say a was 2. Then as you're getting closer to 2, x could be, for example, 1.9. That's close to 2. But what about if you want to get closer? You could pick 1.99. How about if you want to get closer? You can do that, and you can keep doing that as you get closer to 2 from the left. Okay, what's going to happen to the graph? It's either going to increase or decrease. Increase means it's going to get really big, or decrease means really small when we say without bounds. Okay, so either it's going to go, the graph is going to look like this, it's going to go up like this, get bigger and bigger really, really fast, or it's going to go down. It can't do both. Okay, keep that in mind. It can't do both on this side, but it's going to do one or the other. So let me draw the other one with a different color so you know. It's going to do this. Similarly, as you get close to a from the right, in this example I could pick x is equal to 2.1, or x is equal to 2.01, x is equal to 2.001. So you see you're getting closer and closer to 2 as you're walking along the x-axis and getting closer to 2. Then the function is going to either again increase without bounds. It's going to get really big, or then it's going to get really small. Okay, so we need to trap that, figure out which way it is, but we at least know what's going to happen there. From either side, the function's going to get either really big or really small, and I'll show you how to find which way it goes. Okay, whether it goes up or whether it goes down from the left, or whether it goes up or it goes down from the right. So I'll show you how to do that, but the key thing is that's how it's going to do, and I'll show you why that happens. Okay, so let's say, give you an example. Let's say my function f of x is 1 over x minus 2. Okay, and I'll tell you for now my vertical asymptote for this problem is x is equal to 2. So let's just draw a line here at 2. This is 1 and 2, so we're going to draw a vertical line at 2. This is the line x is equal to 2. Okay, so now let's see what happens. According to the definition of vertical asymptote, what's supposed to happen? As you get closer and closer to 2, the value of the function is supposed to get bigger and bigger. Similarly, or smaller and smaller. And I'll prove to you that that's what happens. Let's take out our calculators and check. Okay, alright, so in this case, let's clear this out. There's a way to enter a function by going to y equal to, and then going 1, divided by parentheses x minus 2, close parentheses. You just enter the function where you have it. Then you go to table set. So this is this key up here. So you go second and table. And if you notice, in my case, my independent variable is set to auto, then the calculator is automatically going to pick those. But I don't want to do that. I want it to go to ask. So let's go to ask and press enter. So make sure you guys do that. Okay, so your independent variable x and your dependent variable is y, or f of x. So we're going to quit here. Then we're going to go to table here. So you go second and take graph to go to table. So now you can type in the value. So let's see. What do we want to do? We want to see what happens when we get closer to 2 from the left. So let's pick values of x close to 2. What did I say? 1.9. What happens to y? It's minus 10. How about 1.99? It's minus 100. How about 1.9999? Whole bunch. Okay, it's minus 10 raised to 5. So you can see what's happening. As you're getting closer and closer to 2, the value of the function is getting smaller and smaller because it's negative. So it's negative 100, negative 1,000, negative 10,000, and so on. So you can see the graph as x gets close this way, the graph is going this way. It's getting smaller and smaller, and it's getting big really fast. When we were up to 1.999, it was already minus 1,000. Okay, so you can see it's going to negative infinite. The graph is getting smaller and smaller. These are all the negative y values here. Okay, now what happens if you come from the right? We already know what happens. You come from the left. You can only do one. It can't, if you're coming from the left, it can't go down and go up. Remember, it can't do that because then it's no longer a function. For something to be a function, it can only do one or the other. So let's see if you're coming from the right now. Okay, so I can pick what? 2.1. So it's 10. If I pick 2.01, it's 100. If I pick 2.001, it's 1,000. If I pick 2.0001, then it's 10,000. So you can see as you're getting closer and closer to 2 from the right, the values of the function are getting bigger and bigger, and they're going positive. So in that case, the graph's going like this. So you already know how it's behaving around your asymptote. So that's what happens at an asymptote. Things tend to blow up. Either they get really big or they get really small. And you can see that from the calculator, and you saw that on the graph. So how do we find the vertical asymptote? I already told you what it was in this case. Okay, but let me show you how you find the vertical asymptote. Okay, so finding. Before I go any further, let me go ahead and create that table here just to show you. If this is x, this is f of x. If I pick 1.9, it was a minus 10. If I pick 1.99, it's a minus 100. If I pick 1.999, it's minus 1,000. So you can see the values are getting smaller and smaller as you're approaching 2 from the left. As you approach 2 from the right, you pick 2.1, it's plus 10. Okay. If you pick 2.01, it's 100. If you pick 2.001, it's 1,000. And you can see the values are getting bigger in the positive sense. So they're going to positive infinite. So these are going to positive infinite. Sorry, and these are going to negative infinite, because they're getting bigger and bigger in the positive direction. These are getting smaller and smaller. They're getting smaller as you go in the negative direction. Okay. So how do we find the vertical asymptote? It's really simple. All you have to do is find the values of x for which the denominator is 0. Okay, all you have to do is take your denominator, set it equal to 0, and solve, and that'll give you the values of x for which you have a vertical asymptote. So that's how you find a vertical asymptote. Okay? Alright, let me give you an example. Let's say if I have f of x is equal to x plus 1 over x squared minus 3x. I want to find the vertical asymptote for this. So all you have to do is to find the vertical asymptote. You take your denominator, which is x squared minus 3x, and you set it equal to 0, and you solve. It's degree 2, so I can solve by factoring or by quadratic formula. So I'll solve by factoring, take out an x, you get x minus 3 is 0. This product is 0, one of them has to be 0, so you get x is equal to 0 and x minus 3 is 0. So we get x is equal to 3. So my vertical asymptotes are these two lines. So in this case, the vertical asymptotes are x is equal to 0 and x is equal to 3. So we have two vertical asymptotes. Okay. Now remember, the graph can never cross the vertical asymptote. That means there's no way you can have the graph go like this, because that means there's a point here. That means when x is 2, y must have some value. It looks like it's like minus 10 or something. Okay, but you can see clearly that's not possible, because if x is 2, we get 2 minus 2 is 0. Can I divide by 0 in algebra? No. So that clearly tells you that x cannot be 2, so the graph can never cross the vertical asymptote. It can get closer to it. As you go out, it'll get closer and closer to it. That's what an asymptote basically is. An asymptote is an imaginary line to which the graph gets closer and closer to, as in this case, as x values get closer and closer to 2. Okay, that's what an asymptote is. So I showed you how to find the vertical asymptote. I gave you an example. So now let's take a look at how to find the horizontal asymptote. Talk about the horizontal asymptote. Okay, so in this case, the line y is equal to b is the horizontal asymptote. Okay, and that's the same thing as out here. It was x is equal to a. Okay, so same thing. If the graph approaches the line as x values get very big or very small. So this, in essence, the horizontal asymptote captures the extreme behavior of the graph. How does a graph behave when you go all the way to the right of the graph and when you go all the way to the left of the graph? That's exactly what we did when we did polynomials, if you recall. Okay, so that's what this captures. So let me show you graphically what happens. So you might have a line y is equal to b is a horizontal line because y values always be on that line. So let's say this is my line. This is b. So what the horizontal asymptote traps is the extreme behavior. What happens when x gets really big, so the x values are getting bigger and bigger, or what happens when x gets really small, when they're getting smaller and smaller. Okay, how does the graph behave? Does the graph shoot up or go down, or does it approach a line? If it approaches a line, then that line is called the horizontal asymptote. So it can approach the line like this from the top. Okay, as x gets bigger, the graph will get closer and closer to this imaginary line. Okay, so it's settling down, so eventually the value of the function is going to be b, sort of. It was going to approach b, or it can approach the function from the bottom like this. Okay, and same thing on the left, the graph can approach the function from the top, or it can approach the function from the bottom. Okay, so that's what the horizontal asymptote captures. It captures the extreme behavior. What happens when the function values get really big or when the function values get really, really small. Okay, so I'll give you an example. So let's say that if I have f of x is equal to x over x plus 2. Okay, now I'll tell you here the horizontal asymptote for this graph is y is equal to 1. So what that means is this is 1 here. Okay, so what that basically means is that as x gets bigger, okay, as x values get bigger and bigger, I'll just put goes to infinite, and x gets small when x goes to minus infinite. How does a graph behave? Does it settle down according to this? Since I gave you the answer, it settles down to 1. That means it gets closer and closer to 1. So let's test that. Let's get a calculator out and see. So what do we want to do? I'm going to define that function again. Okay, I'm going to clear that. I'm going to go x divided by parentheses x plus 2. Okay, then I'm going to go to second and table. Okay, so I'm going to enter values of x that are really big. So let's start with 100. If x is 100, what is y going to be? 0.98. That's pretty good. How about 1,000? It's 0.998. How about 10,000? It's 0.9998. So you can see as x is getting bigger and bigger, what's happening to the function? It's getting closer to 1. Okay, and in this case it can either come from the top, it can get closer to this value 1 from the top, or it can get closer from 1 from the bottom. In this case I can tell you it's going to be from the top, and I'll show you how we know that later. So it's coming like this. So as x is getting bigger, the function's going that way. Similarly, when x gets smaller, when you go to the negative side, so you take like minus 10, the value is 1.25. How about minus 10,000? It's 1.002. So you can see as you get closer to 1 from the left, as x values get smaller, as x values are getting smaller, what's happening to the function? It's approaching 1, and this time it approaches 1 from the bottom. And again, I'll show you how to figure that out. For now, let's just assume it does that. Okay, it approaches 1 from the bottom. The key thing is as x is getting smaller, the values of the function are approaching a fixed point 1, and you can see that from this little table. Okay, so now we know what a horizontal asymptote is. How do we find it? So let's do that. If you remember, since the horizontal asymptote deals with extreme behavior, how did we do the extreme behavior when we did polynomials? We kept the dominating term, right? So we do the same thing over here. To find the horizontal asymptote, just keep the dominating terms in the numerator and denominator. So you not only keep the dominating terms in one polynomial, but both the top and the bottom, because we're talking about rational functions. We have polynomials on the top and polynomials on the bottom. Okay, and that's pretty much all we need to do, and check the behavior. Okay, and dominating on top and the bottom. So let me give you an example. Let's go back to the previous example. We had f of x was what? X over x plus 2. So I want to find the horizontal asymptote. Okay, my horizontal asymptote is the line y is equal to something, right? So I keep the dominating terms on the top. On the top it's just x. Out here the dominating term is x, because as x gets bigger, it's going to be much bigger than 2. So these cancel, so we just get 1. So this implies my horizontal asymptote is y is equal to 1. That's all we have to do. Okay, here's another example. Let's say if I have a function like this, I have x squared over x cubed minus 8. Okay, and I want to find the horizontal asymptote. So to find the horizontal asymptote, we keep the dominating term, so we get x squared on the top and x cubed on the bottom. Okay, let's throw in a 3 and a 6 here. So we get, these are my dominating terms. So they reduce, x squares cancel here, and 3 goes into this 2 times, so we get 1 over 2x. Okay, now what happens to this fraction? The asymptote is a line, it's a horizontal line. This is not a horizontal line. So what's going on here? Well, we also have to figure out what we're doing, we're trying to find out what happens when x gets really big. What happens when x goes to infinite? This denominator is going to go to infinite because 2 times infinite is infinite. If you have 1 over infinite, what is the fraction going to be roughly? It's going to be equivalent to 0. Think about it. If you take a number and divide it by the biggest number in your head, the value of that fraction is going to be really small, and you can do that on your calculator. So for example, if I take, let's say the number was 5, and if I divide that by 10,000, what is the value? It's 5 times 10 raised to negative 6. Okay, so it's 0.00050 zeros and a 5, so that's what it is. Okay, so you can see it's almost 0. So anytime you divide a number by infinite, in essence, the value of that is going to be 0. So in this case, the horizontal asymptote is y is equal to 0, because this fraction is getting smaller and smaller. Okay, so that's how you find horizontal asymptotes, and we'll take a look at that. Now there's 2 things you need to know. A graph can cross the horizontal asymptote and not the vertical. Okay, so keep that in mind, and we'll talk about how to check that in a second. Okay, but let me talk about the slant asymptote first. Okay, now that you understood horizontal asymptote, the slant asymptote is the same thing. Okay, the line y is equal to mx plus b is the slant asymptote if the graph approaches the line as x values get very big or very small. So this time it's going to be a slant line because it's not going to be a horizontal line. So the idea is still the same. It still captures, that is, captures the extreme behavior. Now keep in mind, a graph can only have one extreme behavior. That's why a graph cannot have both a horizontal and a slant asymptote, because they both capture the same thing. So either it can have a slant asymptote or a horizontal, not both. Always remember that. Okay, so this is what it looks like. So a slant asymptote might look like this. It's a diagonal line, and we draw a dotted line to indicate it's like an imaginary line. So what will happen here is the graph might get closer to this line like this from the bottom as x gets really big, goes to infinite, or it can get closer to that line from the top. We don't know which way, and again I'll talk about how to find those directions in a second. Similarly, when x gets really small, as the values of x go to minus infinite, the graph can get closer to the line from the top here. It can get closer and closer to that line, or from the bottom. But the bottom line is, as you go further away to the right or the left, the graph is approaching this dotted line. Okay, so that's what a slant asymptote is. Now how do we find the slant asymptote? Okay, to find the slant asymptotes, the slant asymptote is the line y is equal to q of x, where q of x is the quotient obtained by dividing the rational function. So if you divide the rational function, because a rational function has a numerator and a denominator, because you have a polynomial on the top and the bottom. So if you divide the polynomial on the top by the one in the denominator, you'll get a quotient, and that quotient is your slant asymptote. So here's an example. Let's say if I have f of x is equal to 2x squared minus 3x over x plus 1. Okay, So to find the slant asymptote, we do long division. We have x plus 1. We have 2x squared minus 3x plus 0. There's a term missing. Now since the degree of the divisor is 1, I could have also done synthetic division. I hope you guys follow that. I'm just going to do long division. I'm going to multiply this x by 2x. So we get 2x squared plus 2x. Then we subtract the two polynomials. We distribute the negative. So this positive becomes negative and it cancels. This becomes negative, so I get 5x plus 0. Then we multiply by minus 5, so you get negative 5x minus 5. Subtract the 2, so you get 5. X cannot be multiplied by anything to make it into a 5, so that's my remainder. This is my quotient, so my slant asymptote for this problem is y is equal to 2x minus 5. Okay. You know how to graph that line, correct? We have 3 different ways to graph a line. We can either find 2 points on the line by randomly picking 2 x values, or we can find the x-intercept and y-intercept for this line and graphing them, or we can use a slope and the y-intercept to graph them. Okay, so that's what a slant asymptote is. Alright, so graphically I already showed you what it looks like, and I'll show you how to find it. So now let me just give you 2 notes about slant and horizontal asymptote. Notes about horizontal asymptote and slant asymptote. Since you can only have one or the other, how do you know which one do you have? If the degree of the numerator, I'll just put D, E, G, and R, if it's greater than or equal to the degree of, if the degree of the numerator is exactly 1 more than the degree of the denominator, then we have a slant asymptote. So the only time we have a slant asymptote is if the degree of the numerator is exactly 1 more than the degree of the denominator. If you go back to the previous example, the degree of the numerator was 2 and the denominator was 1. So the degree of the numerator was exactly 1 more than the degree of the denominator. The other thing to note is, and if you don't have a slant, then you're going to have a horizontal in these cases. You don't have to have both. Sometimes you might have neither. Okay, just keep that in mind. But usually for our problems, either you're going to have a slant or a horizontal. The other thing to note is a graph can cross the horizontal asymptote or the slant asymptote, but not the vertical asymptote. The graph can never cross the vertical asymptote, because to cross the vertical asymptote you'd have to plug in a number for x for which you'll end up with division by 0, and then think that's not possible. You cannot divide by 0. Okay, so just keep that in mind. Alright, the next thing we want to do then is we want to, if it crosses the horizontal asymptote, how do we know where it crosses the horizontal asymptote? Do you guys follow? Since we know that the graph can cross the horizontal asymptote, how do we know that? Okay, so let's take a look at it. To find the point where the graph crosses the horizontal asymptote or the slant asymptote, solve the equation my function f of x is equal to the horizontal asymptote or the slant asymptote. So we solve this equation. Okay, and I'll give you an example of that so you'll be able to see. Well, let me go ahead and give you one right now. Okay, so for example, let's say f of x is equal to 2x plus 3 over x squared plus 1. Okay, what does this have in terms of slant or the horizontal? Since the degree of the top is 1 and the bottom is 2, it actually has a horizontal, because to have a slant the degree of the top has to be 1 more than the bottom. So to find the horizontal asymptote, what do? We keep the dominating term. So I'm going to write f of x as y. The biggest term on the top is 2x and on the bottom is x squared. So one of these x's cancel. So you're down to 2 over x. Okay, so the dominating terms on the top and the bottom are 2x and x squared, so we get that. What happens to this fraction as x gets bigger and bigger? Just imagine in your head what's happening as x is getting bigger and bigger. It's 2 over 1,000, 2 over 10,000, 2 over 100,000, and so on. You can clearly see this fraction is getting smaller and smaller, so it goes to 0. So my horizontal, this implies my horizontal asymptote is y is equal to 0. So now, to find out if the graph crosses the horizontal asymptote, what do? We take the function and set it equal to the horizontal asymptote. My function is 2x plus 3 over x squared plus 1. You set it equal to 0. This is kind of 0 over 1. You can think of it as that. And we solve for x. So we cross multiply. So we get 2x plus 3 times 1 is just 2x plus 3. And 0 times this is just 0, so we get x is equal to negative 3 halves. So what this means is when x is negative 3 halves, the graph is going to cross that horizontal asymptote. So it's going to look something like this. So let's say this is my horizontal asymptote is 0. Remember, it's this line. So this is my horizontal asymptote. It's the same thing as the x-axis, because it's 0. Y is always 0. The only place y is 0 is on the x-axis. Every point on the x-axis has a y value of 0. So that's my horizontal asymptote. Okay. Now what do we know? That the graph crosses the horizontal asymptote when x is negative 3 halves. So this is minus 1, minus 2. So right here is where the graph crosses the horizontal asymptote when x is minus 3 halves. So the graph might look something like this. It might come out here, then it might cross, and then it might turn, and still it eventually has to hug that horizontal asymptote, because we know that y is equal to 0 is the horizontal asymptote, so eventually the graph has to get closer and closer to that line. Okay, so in this case it crosses the horizontal asymptote and gets closer and closer to that line. So this is where it crosses. So now we have a lot of information. Let's see if we can start applying some of this information to graph some rational functions. So let's get started. So I'll do 3 examples. Okay. So let's say if I have f of x is equal to this, okay, and I have x squared minus 1 over x plus 2. Let's make it 3. Okay. Now, the first thing you do is try to simplify this. So to simplify this, you just factor. So this factors into x minus 1 and x plus 1. And this factors into x plus 3. Nothing cancels, so there's nothing I can do here. But if something did cancel, you want to cancel it out, okay? Then the next step is to find the x-intercept and the y-intercept. So let's find the x-intercept. To find the x-intercept, we set y to 0. Remember, f of x is the same thing as y, so we set that to 0. So we get x squared minus 1 over x plus 3. This is over 1. You cross multiply to solve for x. 0 times this whole thing is 0, and 1 times this whole thing is just that. Then you solve for x. It's square in a number, so move the number to the left hand side and take square roots. So I got 2 x-intercepts here. Okay, so my x-intercepts are x is 1, y is 0, and x is minus 1, y is 0. It's a good idea to just put everything down on the side and box it. Now, if one of these x-intercept had multiplicity, then I would go ahead and write down whether it turns there or flattens there, and I'll take a look at an example of that type too in a second. The next thing I want to do is find the y-intercept. We set x to 0. So we get y is equal to 0 minus 1 divided by 0 plus 3. So we end up with minus 1 over 3. So my y-intercept is x is 0 and y is 1/3. Okay. Then we find the vertical asymptote. Okay. The vertical asymptote occurs whenever the denominator is 0. So you take your denominator, which is x plus 3, and set it equal to 0. So we get x is equal to minus 3. So there's my vertical asymptote. Then you have to decide whether we have a horizontal asymptote or a slant asymptote. Now to have a slant asymptote, the degree of the numerator has to be exactly 1 more than the denominator. Degree of the numerator is 2 and the degree of the denominator is 1. So that is exactly what we have. So we don't have a slant horizontal asymptote, we have a slant. And to find that, we have to do long division. So let's do that. So we have x squared, there's an x term missing, so we'll put 0x minus 1 divide by x plus 3. So what do we do? Find out how many times does x go into x squared? X times. So x times x is x squared plus 3x. Subtract the two polynomials. This is positive, becomes negative. Negative thus cancels. We get 3x minus 1. How many times does x go into that? Negative 3 times. So you get negative 3x minus 3. Okay. Minus 9. You subtract the 2, thus cancel, so you get negative 10. There's nothing you can multiply x by to make it negative 10, right? So you're done. Here's my quotient. That's what we are interested in when we do slant asymptote. So my slant asymptote is x minus 3. And that's pretty much it. The only other thing to do is, before we start graphing, is just check to see if the graph crosses the slant asymptote. So you take your function and set it equal to your slant asymptote. My function is x squared minus 1 over x plus 3, and set it equal to x minus 3 over 1 technically. I'm taking my function and setting that equal to my slant asymptote. Now we cross multiply, so we get x squared minus 1, so you multiply this, so we get x squared minus 3x plus 3x minus 9, so this cancels. And so does the x squared cancel. So we end up with negative 1 is equal to negative 9. Is that a true statement? Is negative 1 equal to negative 9? No. So that tells me that it's not possible. There's no x value for which these two are going to be equal. So anytime you get something inconsistent, so you know that's not true, so it doesn't cross the slant asymptote. So this implies does not cross the slant asymptote. Okay, so that's a nice piece of information to you know. So let's graph this. Okay, it's very important that you label everything with this, since there's a lot to do here. So I'll scale by ones. You can scale by however you want. Okay. Alright, so let's start from the top. Our vertical x-intercepts were 1, minus 1. So that's my x-intercept. My y-intercept was 0 and negative 1/3. Okay, so that's somewhere out here. Okay, my vertical asymptote was x is equal to negative 3. So that's this line. So vertical asymptote going. So this is x is equal to negative 3. The slant asymptote was this line. And to do this, I need x-intercept. What is the x-intercept? You set y to 0. So if this is 0, you move the 3 over. So my x-intercept is 3, 0. And to find the y-intercept, what do? We set x to 0. So we get y-intercept is 0, negative 3. So these are just there to plot that line. I need 2 points to plot that line. So I found the x-intercept, which is 0, 3. 3, 0. And the y-intercept is 0, negative 3. So if I connect these 2 points, I get my slant asymptote. So there you go. That's all we have so far. So now, how do we draw the graph? Well, when you draw the graph, like I said, if you remember, I told you you might sometimes have to pick you may need to pick extra points to guide the graph, and in this case we will have to do that, okay, on one side at least. Okay, so let me show you where. Alright, first of all, let's do coming from the left here. Okay, I don't know where the graph is going to go. Let me just show you some options we have. The graph can go like this, because it can start out here, it can go like this, or it can start in here and go like this. Remember what happens when you get close to the vertical asymptote. Either the function is going to get really big or it's going to get really small. Those are my two options. And then it's going to turn and go like this. Now think about this. Those are my two options. I've drawn them for you. Which one do you think it is out of the two on the left there? Well, if it was this option, if it's going to get really big as you get closer to -3, then it would have to cross the x-axis. Then I would have another x-intercept, right? Do I have another x-intercept? No. So you clearly know it's not this case. So that means it must be this. So the graph starts out here at the bottom as you get close to -3, then it goes out here, and then as x gets smaller and smaller, as x goes in this direction, the function's going to hug that slant asymptote, because that's what it does. It's the extreme behavior. It's going to hug that slant asymptote. So that's what that graph looks like. Okay, so let me go ahead and draw that. So we didn't have to pick any points. We were just able to use a little bit of common sense to do this, because we know what happens close to the vertical asymptote. As you get close to 3 from the left, the graph is either going to go up or it's going to go down. Okay, and if it goes up, then it has to eventually hug the slant asymptote. So eventually it would have to cross the x-axis, and I would have another x-intercept, which I don't have. So it tells me it's not going to do that. So it must do this. Okay, now what happens on this side? Okay, on the right of the asymptote, you always start at the asymptote and work your way out. Always do that. Okay, so I started this asymptote. Well, in this case, the graph, as you get close to -3 from the right, the graph has to be either up here or down here. Those are my two choices. And clearly, if it's down here, then the graph is going to go like this, and it's going to hug the slant asymptote. So if it does that, then it's going to have an x-intercept somewhere here, which I don't have one. I have my x-intercepts in the middle, so that tells me the graph must start up here and go through this x-intercept, go to this y-intercept, go through this x-intercept, and hug that line. And we know it never crosses the slant asymptote, because we already figured that out. So there's your graph of that function. It's a fairly complicated graph, and we were able to do this by just using the ideas of vertical asymptote, horizontal asymptote, and so on. Okay, let me go ahead and give you another example and show you some more example where we can do the horizontal asymptote. So let's do that. So let's say that if you have a function like this, we have x squared divided by, let me pick something nice. Let's say we have x squared minus 4x plus 4 divided by x squared minus 1. So this is a rational function because you have a polynomial on the top and polynomial on the bottom. So the first thing we want to do is figure out, simplify it and cancel whatever cancels once we factor. So if you factor the top, it's got 3 terms, and I'm just going to do it. You guys should know how to do that by now. You get x minus 2 and x minus 2. On the bottom we get x minus 1 and x plus 1. Nothing cancels, so we don't need to worry about it, and I'll do one example at the end where something will cancel, so you can see that. So then we want to find the x-intercept. To find the x-intercept, what do? We set y to 0. This is y, correct? So we set that to 0, so we get x squared minus 4x plus 4 divided by that. This is over 1, so we can solve by cross multiplying. 2 fractions equal. So we get x squared minus 4x plus 4 is equal to 0. We know how to solve this either by factoring, which we already did up here, or by using the quadratic formula. So I'll factor. So this, this product is 0, so one of them has to be 0. So I get x minus 2 is 0, so I get x is equal to 2. I get x minus 2 is 0, so I get x is equal to 2. So what is this telling you? My x-intercept happens to be 2, 0 with multiplicity 2 because it's repeating. Do you guys see that? What happens when an x-intercept repeats? The graph turns there. So that's something we need to look for this time. Okay? Alright, we did that. Now to find the y-intercept. How do we find the y-intercept? We set x to 0, so we get y is equal to 0 squared minus 4 times 0 plus 4 divided by 0 squared minus 1. Okay, so we end up with 4 over minus 1, so we get 4, so negative 4, I'm sorry. So the y-intercept in this case is x is 0, y is negative 4. Okay, we're done with that. Since it's a rational function, we have to find asymptote, so let's do that. The vertical asymptote is what? Whenever the denominator is 0, so you take your denominator and set it equal to 0, square in a number, so you move the number over, and take square roots on both sides, so we introduce plus or minus, so we get this. So I have two vertical asymptotes now. Okay, then we have to decide whether we have a slant asymptote or a horizontal asymptote. So let's go back and check the degree. If the degree of the numerator is exactly one more than the bottom, then we have a slant. In this case, the degree of the numerator and the denominator are the same, so we must have a horizontal asymptote. So to find the horizontal asymptote, what do? We keep the dominating term. What's the biggest term on the top? X squared. What's the biggest term on the bottom? X squared. And when I say biggest, I'm talking about when x gets bigger, if the biggest number you can imagine in your head, if you take that number and square it, that's going to be bigger than any other numbers on the top. So that's what I mean by dominating terms. The x's cancel, so we just get a 1. So the horizontal asymptote is the line y is equal to 1. Now before we go any further, what else do we need to do? Find out if it crosses the horizontal asymptote. So how do we do that? We take our function and set it equal to a horizontal asymptote. Our function was x squared minus 4x plus 4 divided by x squared minus 1 is equal to 1. This is over 1 then, because that's my horizontal. We can cross multiply, so we get x squared minus 4x plus 4 is equal to x squared minus 1. These cancel, so we get negative 4x is equal to negative 5 when you move the 4 over, so we get x is equal to 5/4. So this time it does cross this horizontal asymptote when x is 5/4, so roughly 1.25. So that's something we need to pay attention to. So a lot of things happened here, so let's graph it now. We got all our pieces. So this is x, y. We have 1, 2, 3, 4, minus 1, minus 2, minus 3, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, minus 5, and minus 6. So these are the y values. So let's plot our intercepts. The x-intercept was 2 and 0. So that's this point. Okay, that's my x-intercept. And we know it turns us. I'm going to put a t there, not to forget that, because it repeats twice, even multiplicity. The y-intercept was 0 and negative 4, so that's this point. I think that's what it was. Yep. The vertical asymptotes were at 1 and minus 1. So there I have a vertical asymptote right here. Oops. At 1, at minus 1, and at 1. Okay. Then we had a horizontal asymptote at 1 also. Okay. So let's graph that. Okay. Then we knew that the graph crossed the horizontal asymptote when x was what? 1.25. So when x was 1.25, it crossed the horizontal asymptote. So this is 1 and 2 here, half. So it's here is where the graph, I'll use a different color. This is where the graph is going to cross the horizontal asymptote at when x is 1.25. Okay, got everything? Alright, what did I say? Start at the vertical asymptote and move your way right and left. So let's start at the left here. If you're coming towards this side to the vertical asymptote, just draw out some shapes. So the graph is going to go this way or it's going to go this way. Correct? Remember, when you get closer to the vertical asymptote, the graph either gets really big or really small. Now if it gets really big, the graph's going to go like this. If it gets really small, the graph's going to go like this, because eventually it has to hug my horizontal asymptote when x gets small, right? When you get extreme behavior. Which one is the case here? If it goes from the bottom up, that means it crosses the x-axis. Then I would have an x-intercept. Did I find another x-intercept other than this one? No. So that tells me what? It doesn't do that. So it must come from the top. So that's how the graph goes. Okay. So we got that piece done. So now let's see what happens if you come towards -1 from the right. We have to look at both sides of the asymptote. Well, if I come from the right, my choices are again what? I start up here, or I start up here, because either it gets really big or really small. Since I have a y-intercept down here, that tells me I must start at the bottom. So that is a good clue that you start at the bottom. Okay, so I know I'm going to start out here, but if I start out here, then I'm going to go through my y-intercept. Then where do I go? Do I go up or do I go down? Because now when I get close to 1 here, once again the question is, it goes up or does it go down? Well, let's take a look at the possibilities. If it goes up, then it's going to cross the x-axis again. I'll have another x-intercept, and we don't have any. So you know it doesn't go up. So it must go down. So it crosses here, then it goes down. So you can see, you can use these points to guide you. Okay. Now, as you get closer to 1 from the right, where does it go? It either goes down or it goes up. Okay, which way is it? Well, let's think about it. Okay, if it's like this, if it goes down here, then it's going to go up, it's going to hit this, and it's going to turn, and it's going to go down. Well, that's not going to happen, because eventually it has to hug this line when x gets big. So you know it's not doing that. So it must come from the top. So if it comes from the top, it has to go through this point, because we know my graph crosses the asymptote here, and then it has to turn here. So let's do that. So it's going to come from the top. It's going to go through this point where it crosses the horizontal asymptote, then it turns here, and then it's going to hug that line. So that's what that graph looks like. And that is an extremely complicated graph that was done very quickly by just using the ideas of asymptotes and stuff. Okay, so when you're doing these graphs, just pay attention to the points where they're laid out and use a little bit of common sense reasoning to figure things out. In this case, we knew, and always start at the vertical asymptotes from both sides. We knew either it goes up or down, and if it starts out here, it'll have to have an x-intercept, which we didn't find. So it must be this case on the right side, on the top. Same thing over here on the right here. We knew either it was coming down this way or this way on the top. We knew it couldn't come down this way, because then if it hits the x-intercept, it'll turn and go down, and we know it's supposed to hug it. So those are the kind of just a little bit of common sense that helps us guide that. If you're not sure, what you can do is, once you graph it, just pick a point here. Let's pick 3 and see what happens. So let's plug in 3 into our function. So let's define that function again. My function was what? X squared. So we had x squared minus 4x plus 4 divided by x squared minus 1. Okay, so I'm going to go to my table. Okay, and I'm going to pick some values just to show you. Let's say if I picked -2, just to see where the point is, to make sure our graph is correct. So let's pick -2. Y is -4, so you can see if x is -2, it would be up here somewhere. The point, it's not scaled correctly, and my graph is not very accurate, but the key thing is the y value is above the asymptote, so we know the graph is going like this. Okay, on the other hand, if I pick a value between -1 and 1, so let's say pick -0.5, I should get a number that's below -4, so something less than -4. So we get -25, so that makes sense. The graph must be down here. If I pick a number 0.5, I should again get a number, because it's going to come out here and turn, so I should get a number less than that. In this case, I'm not 100% sure, because it could have done this and then come down. So, but we can check it though. Oops, I said 0.5, right? So it's 10. Okay, so that agrees with our graph. Then we come over here, we can pick 3. If I pick 3, then the graph is between 1 and 0. You can see this is 0, this is 1. So the y value is between 1 and 0. So we can check that. If we pick 3, we get minus 0.111. So you can see that that's correct. That's between 1 and 0. Actually, hold on. What did I do? If it's 4... Oops, I made a mistake somewhere. Let's see, where did I make a mistake? Because it's giving me, you can see the graph is giving you negative values. Is that okay? And it has to be between 1 and 0. Okay. So did I enter that right? We have x squared plus, no, that's right. My horizontal asymptote was x dominating terms, that's 1, that's correct. And it's going to cross at 1.25. So what's going on here? If I pick 5, oops. Let's just graph this. Let me just graph this function to see what it looks like. Zoom, standard. So it goes down, that's correct. Then it goes up. There's vertical asymptotes there, so it is coming from the bottom. And is my horizontal asymptote minus 1? It is 1. And I'm graphing some, because it looks like my horizontal asymptote is minus 1. But from this graph you can clearly see the horizontal asymptote is 1. Okay. So why is this acting so finicky here? That's strange, because it's showing my horizontal asymptote as minus 1 and it should be plus 1. Okay. So let me scale this down. Let's pick 5, delete that. And this is good things, you know, we all make mistakes and we just want to check to make sure that we're doing this correctly. Okay, it's a good idea to always check your work. That's correct. There's a vertical asymptote at 1. There's a vertical asymptote at 1. Okay, then it's turning here and then it's going to minus 1, which is really strange, because when you go there, if I enter a really big value for x, like 100, I should get negative 1. See, it's going to negative 1. And according to us, we went to positive 1. We kept the dominating terms on the top and the bottom. The dominating term is x squared, x squared. They cancel, so we get 1. I am confused why my calculator is doing what it's doing. I wonder if I entered that sign wrong. Insert minus 4x plus 4. Let's try that now. That's better. There we go. So that's the right graph. I used a little minus sign instead of the big minus sign. So, alright, so that's correct. Alright, let me do one more example where the things cancel so you guys can see that. So let's say that I have f of x is equal to x squared minus 1 divided by x squared minus x minus 2. Okay, so in this case I want to graph this rational function polynomial on the top and bottom, so I factor the top 1 minus x, 1 plus x, and I factor the bottom. I get x minus 2 and x plus 1. You can see two numbers, when you multiply you get negative 2. Negative 2 times 1 is negative 2, and when you add you get negative 1. Negative 1, negative 2 times 1 is negative 2 plus 1 is minus 1. So these cancel, so we are down to this. So once we simplify this, this is what we are graphing, not this. Do you guys follow? Because we simplified it. So let's graph that. So let's find the x-intercept. How do I find the x-intercept? We take our y value, this is y, and we set that to 0, so we get x minus 1 over x minus 2. We cross multiply, so we get x minus 1 is 0, so we get x is equal to 1. So my x-intercept is 1 and 0. To find the y-intercept, what do? We set x to 0, so we get 0 minus 1 over 0 minus 2, so we get 1 half. So my y-intercept is 0 and 1 half. Okay, just so you know, we always found a y-intercept. In this case, we can also, if you know, it could have been 0, 0, 2. So just, you know, the y-intercept could have been the origin if I didn't have this minus 1 here, for example. Okay. Alright, so let's go ahead. Actually, I'm going to go ahead and change the problem a little bit. That way we get something different than what we've been working with. Okay, it's still going to be the same. Okay, so I'll do this. I have x squared minus x minus 2, and on the top I'll have 2x minus 2x squared minus 4x. So if I factor the top, I can take a 2x out, so I get x minus 2, and on the bottom I get x minus 2 and x plus 1. So this cancels, so I end up with 2x over x plus 1. So that's a more interesting problem. So I have 0 is equal to 2x over x plus 1. This is my problem now. Do you guys follow? Not this. So let's ignore that. So then I cross multiply, so I get 0 is equal to 2x. You divide by 2, so you get x is 0. So my x-intercept is 0, 0. Okay. To find the y-intercept, what do? We set x to 0, so we get 2 times 0 over 0 plus 1, so we get 0. So the y-intercept also happens to be exactly the same. Okay. Now we want to find the vertical asymptote. To find the vertical asymptote, what do? We take our denominator, which is x plus 1, and set it equal to 0, so we get x is equal to minus 1, so that's my vertical asymptote. Okay. And since the degree of the top is 1 and the bottom is 1, we don't have a slant. So in terms of a choice, we have a horizontal asymptote, so we keep the dominating term on the top, which is 2x, and the dominating term on the bottom is x, so the x is cancelled, so we just get 2. So the horizontal asymptote is y is equal to 2. And right away we should check to see if it crosses it. So you take your function, set it equal to the horizontal asymptote, so we get 2x divided by x plus 1 is equal to 2. Cross multiply. Follow. So we get 2x is equal to 2x plus 2. These cancel. So we get 0 is equal to 2. Is 0 equal to 2? No. So that tells me it does not cross. If you get something inconsistent like that, that means there's no way it's going to cross the horizontal asymptote. There's no value of the function that's going to equal to 2. Okay? Alright, so we are done with that. Let's go ahead and graph this. So we have 1, 2, 3, minus 1, minus 2, minus 3. We have 1, 2, minus 1, minus 2, minus 3. I do need to make this longer. So I'm going to scale this differently because I'll go by 2, 4, 6, -2, -4, -6. Okay, my x and the y-intercepts are 0, 0, so they're right here. Nothing fancy there. They don't turn or flatten there since none of them has even multiplicity. The vertical asymptote is at -1. I only have one vertical asymptote. The horizontal asymptote is at 2. So the graph is supposed to eventually hug that line. Okay. Now let's go ahead and graph this. So let's see. Let's just use common sense. You always start with the vertical asymptote from the left. As we get close to -1 from the left, the graph can either get really big or really small. So now think about it. Which one is it? If it's this, eventually it has to hug my horizontal asymptote, so it might go like this. That means we would have an x-intercept. Do we have an x-intercept? An extra one? No, we only had one. So that's not the case. So you know it's going to come from the top and it's going to hug that line. And it's not going to cross the horizontal asymptote since we found it doesn't do that. So that's a left shape. How about the right side? As you come towards -1 from the right, my graph is going to go like this on the top or like this. Which one is it? Okay, let's think about it. If it's like this, it starts on the top, then it has to go through this point because that's my x-intercept. That means it would do something like this. That means it would cross the horizontal asymptote. Does it cross the horizontal asymptote? No. So that tells me it doesn't do that. That means it comes from the bottom here. Okay, so it comes from the bottom. It crosses the x-intercept and the y-intercept here, and then it eventually, when x gets big, it's going to hug that line. Okay, so that's what it looks like so far, and that's good. There's only one thing we need to fix with this graph. Let's go back to the original problem for a second. We were supposed to graph this, but because we simplified and canceled this, we ended up graphing this. So anytime you cancel something from the numerator and the denominator, you have to assume that that's not 0. So we have to assume that x is not equal to 2. Because that's the only way we can cancel, or else we have a 0 out here and we have a 0 out here if x is 2. And then this whole thing becomes 0 because 2x times 0 is 0 and 0 times x plus 1 is also 0. And usually, a lot of the times we are taught in algebra that 1 over 0 is bad, but in essence 0 over 0 is also bad. Okay, so basically anytime you cancel something here like this, you're making a stipulation that x cannot be 2. That means because if x is 2, then 2 minus 2 would be 0. So we want to make sure that x is not 2. So we come back here. When x is 2 here, we cannot have a point on the graph because 2 is not in the domain. Do you guys follow? So we can come out here and draw a hollow circle here. Because 2 is not in the domain, so we need to draw a hollow circle. So that's something we need to do for this graph since we cancel things from the top and the bottom. So I hope this helps you in terms of graphing rational functions. Please remember, when you graph rational functions, we have to follow the game plan that we came up with at the beginning, this game plan. Okay, because we have a polynomial on the top and the bottom, so we will have asymptotes we need to worry about. We don't always have asymptotes, just so you guys know. For example, if I had given you this function, let's say if I give you f of x is equal to 2x over x squared plus 1. Let's find the vertical asymptote. To find the vertical asymptote, I take my denominator and set it equal to 0. Now, this is not possible for a real number. I could get a complex solution. Okay, so if I square a number, so you move the number over, you take square roots, so we get plus or minus I. But we're not remember I told you when we started the section on functions, we're only working with real functions, not complex functions. Complex functions are a whole nother type of problem, and they're much more difficult. So for now, we're only working with real functions, so this is not possible. So that tells me that this has no vertical asymptote. So this problem has no vertical asymptote. It does have a horizontal asymptote. To find the horizontal asymptote, I keep the dominating term on the top, which is 2x, and on the bottom, which is x squared. One of these x's cancel, so I get 2 over x. So when x gets big, this fraction 2 over x gets really small, so my horizontal asymptote is y is equal to 0. Okay, so this problem does have that, and you can convince yourself your x-intercept and y-intercept are 0. So when you look at this graph, my x and the y-intercept are 0. My horizontal asymptote is just the line, the x-axis. So this is my horizontal asymptote. Do you guys follow? Because on this line the y values are always 0. Every point on the x-axis has a y 0. There's no vertical asymptote. So what does this graph look like? Well, eventually we always use the vertical asymptote to guide the graph. In this case there's no way to guide the graph because we don't have a vertical asymptote. But we do have one point where so that also happens to be the point where it crosses the horizontal asymptote. So if you were to take this and set it equal to 0 and solve, you'll find that that's where it crosses the horizontal asymptote. Okay, we have one point. That doesn't help us, but I do know something. Eventually the graph is going to hug this, the horizontal asymptote, when x gets small, from the top or from the bottom. I just need to know which way it's going to hug. So in this case I'm going to have to pick some value to test this function. Do you guys follow? So let's do that. Let's just pick some value to test it. So let's say I pick -5, because -5 would be somewhere here. So if x is -5, you get what? 2 times -5 is -10, divided by -5 squared is 25, plus 1 is 26. We're not interested in the value of the number, we're interested in the sign. The sign is what? Negative. That tells me that when x is -5, the graph is going to be down here somewhere. So it's not coming from the top, it's actually coming from the bottom. So it's going to come like this. Then eventually it has to go through this point. It's not going to turn here because this x-intercept is not special. It's not going to turn. So it's going to go like this, and eventually it's going to hug this again. So once we pick that one point, that helps us finish this graph. Okay, so sometimes you have to pick some values to check it, because you might not be able to start the graph because you don't have a vertical asymptote. But if you do have a vertical asymptote, you can always start the graph correctly then. But out here we just picked x is -5, and we found that the y value was negative, so it was below the x-axis, so that's where the graph was coming from, and that's what it looks like.